Hey pre-calculus students, this is lesson 11 in our first module. In this lesson we're going to calculate the distance between complex numbers by finding the modulus of their difference. So we'll have a nice convenient way to calculate distances. And then we'll also be able to calculate the midpoint between segments of complex numbers by finding the average of its endpoints. So by the end of today, we should be able to find a midpoint and find a distance, and we'll have nice convenient formulas to do that for our complex numbers. This is our first time looking at this new standard, which is to calculate the distance between numbers as the complex planes as the modulus of the difference, and the midpoint of a segment as the average of endpoints. So that standard is exactly our objectives for today. This standard is pretty straightforward. We'll spend about 2 days on it, and then we should be all set. Okay, so for the do now, I gave us what looked like a geometry problem. We have 2 points here. I asked us to find the midpoint of the 2 points and the distance, and up here are our formulas that you may recognize from geometry or algebra classes. So for the midpoint, I notice in both of these formulas, it seems like they're labeling our points x1 and y1, for example. So I'm going to go to my points and I'm going to label this one on the left here, x1, comma, y1, and this one on the right, x2, y2. Now that I know which one's which, I can plug them into my formulas. So for my midpoint formula, it's x1 plus x2 all over 2, y1 plus y2 all over 2. If I plug my numbers in, I'll get negative 5 for x1 plus 2 all over 2, and negative 1 plus x2, which is in red up here, is 3. Comma y1, which is 2, plus y2, which is in red, which is 4, all over 2. Then if we simplify this, it looks like we're going to get negative 5 plus 3, that's negative 2 over 2. So that's negative 2 over 2 is just negative 1. And then for this, we're going to get 6 over 2, which is just going to be 3. So we expect our midpoint to be negative 1, 3. Let's plot it and make sure that makes sense. Negative 1, 3, right there. There's our midpoint. All right. Next, we're going to find the distance. We already have our points labeled. Our formula is right there. Square root of x2 minus x1 plus y2 minus y1 squared. 3 minus negative 5. Notice I added the extra parentheses here when I plugged in a negative number because I knew that I wanted to keep track of that negative sign. Minus a negative, keep parentheses on it, plus y2 minus y1 is 4 minus positive 2 squared. So that gives us square root of 3 minus a negative is 3 plus. That's going to be 8 squared, plus 4 minus 2 is just 2 squared, which is going to be 64 plus 4, which is square root of 68. Okay, so we found here that the distance between these two is square root of 68, and the midpoint between these 2 points is negative 1, comma 3. So we're going to find today that working with complex numbers is a lot like working with our points in the coordinate plane, just like we did here in our do now in geometry. The only thing that's different with complex numbers is instead of writing our points as, say, the point negative 5, comma 2, our complex numbers, we write them as a real part of negative 5 plus an imaginary part of 2. So we write our numbers, the complex ones, as a sum. We don't need to keep them separated by a comma. They're separated by the fact that one's imaginary and the other one's real. So that will come in really handy, and it's going to allow us to get much simpler formulas for our midpoint and distance. One thing I wanted to point out here, In our class, we discussed that this setup right here, this formula for distance, looks an awful lot like a formula we've seen for complex numbers. It looks an awful lot like square root of a squared plus b squared, or our modulus. That's just something we noticed as we did this activator, that square root of something squared plus something squared looks a lot like our modulus, which was the length of our vector in the complex plane. Okay, so let's go to our classwork for today. We're going to use those plots to help us. Loading. Okay, we're going to start right off with exercise 2, exercise 1 and 2. So 1 says the endpoints of AB are these 2 points. What would be its midpoint? So again, we could just apply our formula really quickly. I know I'm summing up my x's. 1 plus -5 is -4 over 2, comma, and then for the y's, 8 plus 3 is 11 over 2, which is just going to be -2. And then 11 over 2 we could leave as a fraction, or we could write as 5.5 or 5.5. All right, so now we want to find the midpoint of our complex numbers, but looking at them, we notice they're actually the same. Points in the coordinate plane. If I were to plot 1 plus 8i for a, that's the same as plotting the point 1, 8 in the complex plane. So off the top of our head, maybe it's like, well, if these points are the same, maybe the midpoint that we get is also going to be the same. So maybe we expect that this point, this x comma y, will be the midpoint in our complex plane, and it would have coordinates of real part -2 and an imaginary part 5.5i. So that's maybe how we could write that midpoint as a complex number. But another thing we want to notice here is that what we really did when we found the midpoint is we took the real parts, which I've highlighted in orange, and we added them up and divided by 2. So the real parts need to go add up and divide by 2. But we also added up our imaginary parts, which I highlighted here in yellow. The imaginary parts need to be added up and divided by 2. So we're trying to think of a simple operation we could do with our complex numbers that allow the real parts to add up, and so the orange parts to add up, and also the imaginary parts to add up separately, and then divide it all by 2 to get our midpoint. So because the real parts and imaginary parts stay separate when we add them up, we can just add our complex number a to our complex number b, and just without even doing anything, the real parts and the imaginary parts are going to combine to make our like terms. It's going to combine to -4 plus 11i. So the only other thing we needed to do to find our midpoint was, well, we combined our terms, so just adding up our numbers and then dividing by 2. So throughout this whole thing, divide by 2. So this kind of gave us a really convenient formula. If we want to find the midpoint, we just take our numbers, add them up, a plus b, and divide by 2. So this is the formula we'll be using in this class. And let's look at our standard and our objective today to make sure that this matches what we're supposed to be doing. Our objective said, calculate the midpoint of a segment between complex numbers by finding the average of its endpoints. All right, so if I go down here and look at this number, remember an average of something, if I had like 2 and the number 3, and I wanted to find their average, I would add them up and divide by 2. That would give the average of 2.5. That's exactly what we're doing here with our complex numbers. We're taking our complex number a, we're adding it to our complex number b, and then we're dividing by 2. So we're taking the average. We're finding what's in between a and b. So this formula is really important. Star it, double make a note of it. That's what we're going to be using today on your exit ticket to get to show mastery on this throughout the course. Now in B, in class, we took time and set this up to show that in general that this is true. And that's kind of nice. I'm going to show it briefly here. Our job is saying show in general that the midpoint of A and B is the arithmetic average of the two numbers. The midpoints of A and B is A plus B over 2, the average of two numbers. So our job is to show that our midpoint, what we expected this thing to be, which was x1 plus x2 all over 2 plus y1 plus y2 all over 2I, show that these two things are equivalent. So what we did in class is we went on and we plugged in our general numbers a and b here, which would give us x1 plus y1I plus x2 plus y2I all over 2. And then we notice, well, we're starting to look maybe a little bit more like our the left side. We want to make the left and right sides look the same. What we need to do, though, is get our x's together. They're apart right now. We want to combine those sort of real parts together on one side, and then combine our imaginary parts on another side, separate and solve. I'm not too worried about this right now for the interest of the video, but it was just showing that we can also write in general terms with our formula that these two are the same. Okay, so we know how to calculate midpoint. We'll practice this at the end. Now we want to do the same for distance, and they use the same points, and they want to make this connection that this segment with coordinates, with xy coordinates, is the same as the segment that connects our two complex numbers with the same real and imaginary parts. So for distance, again, our formula was x squared minus x1 squared plus y2 minus y1 squared. So again, we could just match up our terms x1, x1, y1, x2, y2, plug them in and solve. That would be pretty easy. Let's do that really quick. Negative 5 minus 1 plus y2 is 3. Y1 is 8. That's going to be negative 6 squared is 36. Negative 5 squared is 25. That gives us 61. Okay. So we see here, we can use our kind of labeling these as x and y as the similarities to find our distance. But we also notice that this taking square root and something squared plus something squared looks a lot like an operation we've learned before. If we had a number z, oops, I'm going to make a note down here. If we had a number z equal to a plus bi, the modulus of z was equal to the square root of a squared plus b squared. And we see that same structure here. There's a square root of something squared plus something else squared. Here, though, it's not just a and b. It's not just the real and imaginary parts. It's a real part minus another real part, and the imaginary part minus another imaginary part. So it seems like we're subtracting these two numbers. And then we see the modulus happening afterwards. So if I want to write that as a formula, I would say we're subtracting two numbers, b minus a here. B has the x2s, all the x2s. This is from b. And the y2 is from b. And then we're subtracting off all the a's, subtracting the real and imaginary parts from a. So I do b minus a. Then once we had that, it seems like we took the modulus of that number, which we just mark with our little vertical lines. So this will be the formula. Also, we could write it as the modulus of a minus b. We had a discussion in class that if we did x2 minus x1 or x1 minus x2, it won't actually affect our answer at all, because it's just the difference of taking the square, negative 6 squared or 6 squared. So it doesn't actually mess up our numbers. So either one of these formulas is our second thing we need to have for today. And again, here we showed the general case. I don't want us to spend too much time on that. We'll come back to it. But for right now, I want us to just practice using these two formulas now that we have them. So in your summary, here they are again, if you so you can reference back to them in the summary. So this is the last page of this lesson. For two complex numbers, the midpoint of A and B is the sum over 2, or the average of the two numbers. And the distance of two complex numbers is the modulus of their difference, or we subtract them first, then we take their modulus. So let's kind of break these problem down so that we can see these work. So here we're given two numbers, z and w, and it says find the midpoint m of z and w. Okay, so my midpoint formula, I'm just going to say my midpoint, first of all, is going to be, I usually write it as a plus b over 2. I just wrote down a note on my formula. I know it's going to be the average of my two numbers. So what we want to do here then is figure out what our a and b are. Well, let's call z a and call w b. So I'll just rewrite it with those. Z plus w all over 2. All right. Now, all we have to do is substitute what z and w actually are. And again, when I substitute, I really like to just open up spaces where I'm going to plug my numbers in. That's going to help me keep track of my signs. So I opened up spaces. Now I'm going to plug in z is 2 plus 7i, and w is negative 3 plus I, and it's all divided by 2. So that's all set. We just have to combine our terms and simplify. 2 is my real part here. It's going to combine with negative 3. I'm just combining. Notice I'm just adding, so I'm just combining my terms. 2 and negative 3 combine to make a negative 1. And then for my imaginary parts, 7i and I are going to combine to make 8i. And that's all over 2 still. And then if we wanted to plot this, we may want to break our fraction up. When we're dividing by a number like this, we've got to divide both. So if we break this up, it'd be equivalently negative 1 over 2 plus 8 over 2i, which would just be negative 1/2 plus 4i. And you could write this as a decimal too, negative 0.5 plus 4i. That's fine. Whatever helps you plot it, basically. Now we have the midpoint. Now we could go and plot these numbers and see that indeed m, this number we just found, m, is right in the middle of z and w. So we wrote down our formula, plugged in our numbers, and simplified. Let's do the same. Let's do the distance here. I'm not worried about verifying this one as much. Let's do the distance here. Distance. Again, our formula is going to be the modulus of a minus b. That's right from our summary. Again, here we're going to use our z and w. Just from, we picked z to be a and w to be b. Then we're going to plug in our numbers. Again, it's really important to leave spaces with parentheses because here we have a negative right in the middle, and we're going to have to make sure we're subtracting both the real and complex parts of w, so we need those parentheses. Z is 2 plus 7i, and then w is negative 3 plus I. I'm going to rewrite this right below. Again, when we're subtracting, we got to subtract both the negative 3 and the positive I. So I like to rewrite these with the parentheses off now that we've taken care of the negative. Negative 3 is going to be positive 3, and then negative positive I is negative I. All right, combine our terms, we get magnitude of 5. 7 minus 1 is 6i plus 6i. 2 and 3 gave us 5. Yep. And then 7i and negative I gave us positive 6i. Great. Now we're just finding the modulus of that complex number. We've done this quite a bit before. Here our a is going to be 5, and our b is going to be positive 6. So we'll use our formula, equals the square root of a squared plus b squared, which is 5 squared plus 6 squared. It's going to be 25 plus 36, which is 61 again. And again, you could write this as a decimal if you like. I don't know the square root of 61. Square root of 61, it's going to be, I know it's going to be less than 8 because the square root of 64 is 8. I know it's going to be more than 7. So let's check it in the calculator. It's going to be between 7 and 8. Calculate here, square root of 61 is 7.8, just what we expected, 7.8. Between 7 and 8, a little bit closer to 8 than to 7. Okay, so overall, these are pretty straightforward. It's really just taking our new formulas right here and right here, our new formulas for midpoint and distance, and applying them to our numbers. So when you're ready, come in and take your exit ticket. You should be all set to do that. In intervention, I'm going to put up some of these for extra practice, just to get these skills down, but I will post those in the extra practice section on the website. All right, talk to you later.